Let us look at another example of solving linear programming problems using Simplex method. In this example, we'll look at the special case of multiple optimal solutions. Maxis Manufacturing Company manufactures two products, P1 and P2. Both the products are processed on two machines, M1 and M2. That means P1 has to be processed on M1 and then M2. Similarly, P2 has to be processed first on M1 and then on M2. The data provided is as follows. So, product P1 needs 1 hour of processing on machine M1 and 3 hours of processing on machine M2, while product P2 needs 2 hours of processing on machine M1 and 2 hours of processing on machine M2. Now, the machines M1 and M2 have constraint of availability in terms of number of hours per week. So M1 has an available capacity of 80 hours per week, while M2 has an available capacity of 120 hours per week. Now we have also been given that each unit of P1 generates a profit of 30 rupees, while each unit of P2 generates a profit of 20 rupees. Now we have to find out how many units of P1 and P2 should be produced per week in order to maximize profit. So let us look at how to solve this using Simplex method. Now the first step in solving this example using Simplex method is to construct an LP model of the problem. In this step, we have to convert the given word problem into an LP model. Now in the given problem, we have to find out the quantity of P1 and P2 to be manufactured per week in order to maximize the profit. So let's assume that X1 is the quantity of product P1 to be produced and X2 is the quantity of product P2 to be produced. Now for product P1, the profit has been given as 30 rupees per unit, and for product P2 the profit has been given as 20 rupees per unit. So if 30 rupees is the profit per unit, and if we are assuming X1 as the quantity of product P1 to be produced, then how much is the profit generated for X1 quantity of product P1? So for 1, the profit is 30 rupees. So for X1, how much? Let's say this is Y. So Y into 1, we're doing cross multiplication here. Y into 1 is Y is equal to 30 times X1. Similarly for P2, 1 unit generates a profit of 20 rupees. So X2 numbers will generate how much? Let's say this is again Y, cross multiplication. So Y into 1 is Y, which is equal to 20 times X2. So the profit generated by X1 numbers of product P1 is 30X1, and the profit generated by X2 numbers of product P2 is 20x2. So the total profit for manufacturing both P1 and P2 is 30x1 plus 20x2. And in this problem, we have been asked to maximize the profit. So this becomes our objective function. Next, we'll look at the constraints that have been given to us. So these are the constraints given to us. M1 is needed for 1 hour for each unit of P1 and 2 hours for each unit of P2. And the total number of hours available for M1 are 80 hours per week. This is per week. Similarly for M2 is needed for 3 hours per unit of P1 and 2 hours per unit of P2. And the total capacity or the total number of hours available of M2 per week are 120. So let's first take the constraint of M1. So if one unit needs 1 hour of processing on M1, then X1 units will need 1 time X1 hours on M1. It is similar to X1 because 1 times X1 is X1. Now for P2, M1 is needed for 2 hours per unit. So if the quantity of P2 to be produced is X2, then the total number of hours needed for M1 will be 2 times X2. Now when we add these two, that will give us the total number of hours needed for producing X1 quantity of P1 and X2 quantity of P2 on machine M1. And this should be less than or equal to 80 because 80 is the maximum capacity available for M1. So our first constraint becomes X1 plus 2X2 is less than or equal to 80. Similarly for machine M2, each unit of P1 needs 3 hours on M2. So X1 units will need 3 times X1 hours on M2 plus now each unit of P2 needs 2 hours on M2. So X2 numbers of product P2 will need 2 times X2 hours on M2, and this should be less than or equal to 120. And also we'll have the constraint that X1 and X2 should be greater than or equal to 0. So these are the constraints for our LP model. So we have the objective function here, P is equal to 30x1 plus 20x2, and the constraints x1 plus 2x2 is less than or equal to 80, 3x1 plus 2x2 is less than or equal to 120, and x1 x2 is greater than or equal to 0. Now in order to solve this using the simplex method, we have to make sure that the two conditions are satisfied. The first condition is that the right hand side of each of the constraints should be non-negative. So here we have all the right hand side of the constraints as non-negative. So this condition is met. Now the second condition is that each of the decision variables, that is x1, x2 in this case, should be non-negative. So we have already added that as one of the constraints. So this condition is also met. So now we can proceed with the next step of solving this using the simplex method, which is to standardize the problem. Now in order to solve this using the simplex method, we need to convert the constraint inequalities that is these, into equations. That means having a equal sign. So what this means is we have to make the left hand side equal to the right hand side. Now let's take the first constraint. So this is indicating that the time taken by products P1 and P2 on machine M1 is less than or equal to 80 hours per week. So if it is equal to, then that is great. However, it can be less than. So what that means is that products P1 and P2 may sometimes not be able to consume the entire capacity of M1 of 80 hours. What that means is that M1 may have some unutilized capacity. So if we consider that unutilized capacity as a slack variable S1, then we can write x1 plus 2x2 plus s1 is equal to 80. If products P1 and P2 consume the entire capacity of 80 hours, then s1 will become 0. However, if there is an unutilized capacity, then s1 may have a value. Similarly, for the second constraint, we can write 3x1 plus 2x2 plus s2 is equal to 120, and all these variables should be greater than or equal to 0. So x1, x2, s1, s2 should be greater than or equal to 0. Now we have added two new variables, and all the variables should be included in the objective function. However, we'll consider that the unutilized capacity does not have any impact on the profit. So we'll consider a 0 coefficient for S1 and S2 in the objective function. So our objective function now becomes P is equal to 30x1 plus 20x2 plus 0s1 plus 0s2. So this is the standardized form of this problem. Now let's move to the next step, which is to create the simplex table. Now in the simplex table, the first row is called the objective row. This row represents the profit or cost per unit of each variable in the objective function. This is also known as contribution per unit and represented by Cj. For example, we know that each unit of product P1 gives a profit of 30 rupees. So x1 represents the quantity of product P1 being produced, and the coefficient is representing the profit per unit. So we'll note the coefficients here: 30, 20, 0, 0. Now the second row of the table indicates the variables in the problem for which the Cj components have been written in the first row. So the variables are x1, x2, s1, s2. So let's note that down: x1, x2, s1, s2. Now below the second row, the coefficients of variables in the constraints are noted down. So our first constraint is x1 plus 2x2 plus s1 is equal to 80. So x1, the coefficient is 1. For x2, the coefficient is 2. For s1, the coefficient is 1. And s2 is not present in this constraint, so we'll consider the coefficient as 0. Now for the second constraint, the coefficient of x1 is 3. Coefficient of x2 is 2. Coefficient of s1 is 0. S1 is not here, so we'll consider this 0. And the coefficient of s2 is 1. Now let's move to the next step, which is to establish a basic initial feasible solution. Now the simplex method is based on the premise that the optimal solution in case of maximization objective will occur at one of the corner points of the feasible solution region. So let's say this is the feasible solution region represented by O, A, B, C. So the optimal solution will occur at one of these corner points. So in this method, we basically start at one of the corner points and at each step or iteration move to an adjacent corner point in such a way that the value of the objective for the iteration improves at every iteration. So first we'll start with the origin, which has the variables as 0 and 0. So in our case, we'll consider x1 and x2 as 0. So now with this, let's find the values of s1 and s2. So from the first constraint, if x1 and x2 are 0, then s1 is 80 and s2 is 120. So basically what we are saying is that at this point, the first solution is that we don't produce any of product 1 or product 2. That means the entire capacity of M1 and M2 is unutilized, which is represented by the slack variables S1 and S2. Now the slack variables S1 and S2 with non-zero values are known as the basic variables, while the variables with 0 values, that is x1 and x2, are known as the non-basic variables. So with this information, we can complete the simplex table. So we need to add two more columns here. The first column is represented by CB, and this represents the coefficients of the current basic variables in the objective function, while the second column is the basis column, which represents the basic variables in the current solution. So in the current solution, the basic variables are S1 and S2. So let's note those down. So S1, S2, and the coefficients of S1 and S2 in the objective function are 0 and 0. So we'll note them in the CB column. Now we also need to add another column known as the solution values column, which is represented by B. This column takes the values of the basic variables S1 and S2 in the initial basic feasible solution. Now those values are 80 and 120, so let's note them down. So this completes our simplex table. Now the next step is to perform optimality test on this basic initial feasible solution to find out if this is an optimal solution or not. So let's proceed to step number 5. So in order to perform the optimality test, we have to now add two new rows to the simplex table. The first row is Zj or Zj. So let's add Zj. Elements in the Zj row represent the decrease in the value of the objective function or profit, which will result if 1 unit of the variable in the jth column is brought into the solution or the product mix. So this represents the contribution loss per unit from the introduction of 1 unit of the variable in the solution. Now the way to calculate this is 0 into 1 plus 0 into 3 for x1 column. So this becomes 0. 0 into 2 plus 0 into 2, which again becomes 0. 0 into 1 plus 0 into 0, which again becomes 0. 0 into 0 plus 0 into 1, which again becomes 0. 0 into 80 plus 0 into 120, which again is 0. Next we have to add another row, which is Cj minus Zj. This row is obtained by subtracting column wise the Zj values from the Cj values. And the values of this row will represent the net profit for each unit of the column variable introduced into the product mix. So basically Cj is representing the profit if one unit is introduced in this solution, and Zj is representing the loss. So Cj minus Zj represents the net profit. So 30 minus 0 is 30, 20 minus 0 is 20, 0 minus 0 is 0, 0 minus 0 is 0. Now this row Cj minus Zj determines whether or not the current solution is optimal. So once the values of Cj minus Zj are obtained, they are examined to find out if the solution is optimal or not. In case of all the values are negative or 0, the current solution is optimal. This is because the negative values indicate that if we try to further improve the solution, the profit will be decreased. And a 0 value indicates that even if we bring that variable in the solution, the solution value or the profit value is going to be the same. And in case of any element being positive, the indication is that the solution is not optimal and there is scope for further improvement. So in this example, since we have positive values for column x1 and x2, the solution is not optimal and there is scope for improvement. Hence, we need to proceed to the next step, which is to improve the current solution. Now, since we have positive values for the row Cj minus Zj, which indicate that the solution can be improved further, we observe the values of Cj minus Zj for different columns and mark the column for the maximum positive value. So this is the column with the maximum positive value. Now the variable heading of that column is the one that should be entering the solution. That is, the corresponding product should be produced. This variable is called the entering variable or the incoming variable, and the column is known as the key column. Now we need to find the departing variable, which will be replaced by x1. So in order to do that, we have to find the value of theta, which is known as the replacement ratio column, and is obtained by dividing the elements under column B with the corresponding elements in the key column. So 80 divided by 1 is 80 and 120 divided by 3 is 40. Now the row containing the minimum non-negative ratio is marked. So this 40 is the lowest non-negative ratio, and this row will become the key row, and the variable of this row, that is S2, becomes the departing variable. Also, the element at the intersection of key row and key column becomes the key element, which is enclosed in the brackets as shown. Now after we have selected the key column and key row, a revised simplex table providing an improved solution can be developed. The incoming variable, which is x1, now replaces the departing variable, which is s2, and the coefficient of the incoming variable in the objective function, which is 30, is entered in the CB column. So let's make that change. So here we'll have x1 and this will be 30. Now we need to make this key element as 1. So what we'll do is we have to divide all the elements of the key row by the current key element, which is 3. And then we have to rewrite all these elements. So let's do that. So here I've entered the revised elements in the key row. Now next, for the remaining rows, we have to make the element in the key column as 0. So we already have 1 as the key element, and the remaining elements in the key column should become 0. Now let's see what changes we have to make to the row with variable s1 in order to achieve that. So first, the variable and its contribution, that is the CB column elements, are reproduced without change. All the other elements in the row are replaced by new elements obtained by subtracting a multiple of the reduced key element from the element in this row. So basically what we have to do is 1, this is the one of row S1, minus 1, which is the key element, multiplied by a multiple should be equal to 0. So 1 minus x is equal to 0, or x is equal to 1. So now what we have to do is we have to calculate 1, which is the one of the row S1, minus 1, which is the key element, the reduced key element, into the multiple 1. So this is equal to 1 minus 1, which is equal to 0. So this becomes 0. Now the same multiple has to be multiplied by all the reduced elements of the key row and subtracted from the corresponding elements of the target row. So let's take the example of column x2. So 2 is the element in row S1. So 2 minus the element in the key row is 2 by 3 multiplied by the multiple, which is 1. So this is 2 minus 2 by 3. So 3 is the denominator. 3 into 2 is 6 minus 2. So this is 4 by 3. So this becomes 4 by 3. For the next one, 1 minus 0 into 1, which brings 1. For the next one, 0 minus 1 by 3 into 1, which is 0 minus 1 by 3, which becomes minus 1 by 3. And for B, 80 minus 40 into 1, which becomes 80 minus 40, which becomes 40. So let me replace this row with the new numbers found. So this is the new simplex table with the revised elements which represent the new solution. Now we'll move to step number 7, which is nothing but repeat step number 5 and 6 until we get the optimal solution. Okay, so now we have to again repeat step number 5, which is to perform optimality test on this new solution. So let's find the value of Zj. Now this 1 is no longer the key element, so let me remove this parenthesis here. Okay. So for column x1, 0 into 0 plus 30 into 1, which is 30. For x2, 0 into 4 by 3 is 0. 30 into 2 by 3 is 20. Right? 3 tens are 30, so 10 multiplied by 2 is 20. 0 into 1 plus 0 into 30 is 0. 0 into minus 1 by 3 is 0, and 30 into 1 by 3 is 10. 0 into 40 is 0. 30 into 40 is 1200. Now let's find the value of Cj minus Zj. So 30 minus 30 is 0. 20 minus 20 is 0. 0 minus 0 is 0. 0 minus 10 is minus 10. So here, as we can see, the value of Cj minus Zj are either 0 or negative. So this is the optimal solution because we can't further improve the profit. So here the solution is that x1 is 40 and x2 could not enter the solution mix, so x2 is still the same, which is 0, which we had identified in the basic initial feasible solution. So x1 is 40, x2 is 0, and the solution, that is profit, is equal to 1200 rupees. So we should manufacture 40 numbers of product P1, 0 numbers of product P2. Now, in a graphical method, multiple optimal solution is found when one of the lines making the boundary of the feasible solution region runs parallel to the objective function line. So all the points on the line making the boundary of the feasible solution region become the optimal solution. Now, in a simplex method, multiple optimal solution can be detected by observing a 0 value in the Cj minus Zj row under a non-basic variable. So the 0 value of a non-basic variable in the optimal simplex table suggests that the current non-basic variable can enter the basis or the solution with 0 impact on profit. So that will also give the same solution, say the same profit. Thus, another feasible solution giving the same optimal value of profit is possible, and that becomes the alternate optimal solution. So in our case, we have S1 and X1 in the basis column, while X2 and S2 become the non-basic variables. Now S2 has a Cj minus Zj value of minus 10, which means that if we introduce this in the solution, then our profit is going to reduce. However, X2 has a Cj minus Zj value of 0, which means that this can enter the solution without impacting the optimal solution. So now column X2 becomes our key column, and X2 is the entering variable. Now we have to find the departing variable. So again, we'll find the value of theta. So 40 divided by 4 by 3. This is 40 by 4 into 3. So this becomes 30. And 40 divided by 2 by 3. 40 by 2 into 3. So this becomes 60. So the lowest ratio is 30. So S1 row becomes the key row. and this element here becomes our key element, and S1 is the departing variable. So let's now replace S1 with X2, and the corresponding CB value will become the coefficient of X2, which is 20 in the objective function. So let's do that. Now we have to make the key element as 1. So we'll divide all the elements in this key row by 4 by 3. So 0 divided by 4 by 3 is 0. 4 by 3 divided by 4 by 3 will become 1. 1 divided by 4 by 3 becomes 3 by 4. Minus 1 by 3 divided by 4 by 3. So let's do that. Minus 1 by 3 divided by 4 by 3. Minus 1 by 3 into 3 by 4. Minus 1 by 4. So this becomes minus 1 by 4. And 40 divided by 4 by 3. 40 divided by 4 by 3. So this is nothing but this. So this is 30. So let me replace these elements with the new elements. Now each remaining row of the previous matrix is to be substituted by the new row called replaced row. So basically the idea is that the key element will be 1 and the remaining elements in the key column should be 0. So in order to do that, for the remaining rows, the variable and its contribution, that is the CB column, are reproduced without change. So this x1 and 30 remain as it is. Now this we have to make 2 by 3 as 0. So 2 by 3 minus 1 into x is equal to 0. So x is equal to 2 by 3. Now we have to do the same calculation for all the remaining elements. So 1 minus 0 into 2 by 3 will be 1. This becomes 0. So for column S1, 0 minus 3 by 4 into 2 by 3. So this is minus 1 by 2. Minus 1 by 2. For S2, 1 by 3 minus minus 1 by 4 into 2 by 3. So this is 1 by 3 plus 1 by 6. 6 is the LCM. 2 plus 1. This is 3 by 6 or 1 by 2. So this becomes 1 by 2. 40 minus 30 into 2 by 3. 3 tens are 30. So 40 minus 20. This is 20. Let me replace this row with the new elements, and also let me remove Cj minus Zj and Zj values. So here I have replaced the row x1 with new values. Now let's perform the optimality test on this solution. So let's find the values of Zj. For column x1 it is 30 into 1, which is 30. For x2, 20 into 1. For S1, 20 into 3 by 4. 20 into 3 by 4 plus 30 into minus 1 by 2. So 25, 5 is a 15 plus this becomes minus 15. So this is 0. So this is 0 here. Now for S2, 20 into minus 1 by 4. So this is minus 5 plus 30 into 1 by 2, which is 15. So this becomes 10. So this is 10. and for B 20 into 30, which is 600, plus 30 into 20, which is again 600, so this is 1200. Now let's find out Cj minus Zj. So 30 minus 30 is 0, 20 minus 20 is 0, 0 minus 0 is 0, 0 minus 10 is minus 10. Now since all the values of Cj minus Zj row are either 0 or negative, this is an optimal solution. So the solution is x2 is 30, x1 is 20. So x1 is 20, x2 is 30, and profit is 1200 rupees. So basically we can manufacture 20 units of product P1 and 30 units of product P2 and still we'll get the same profit as 1200. So these are the two optimal solutions for this problem.